Hello, Kim1A. This is Chapter 9, Lecture Video 2. This is our last lecture video. We're going to be covering the rest of the periodic trends here in this chapter, starting with ionization energy. Now, what is ionization energy? It's kind of like the exact opposite of electron affinity, which is one of the trends we talked about in the last lecture video. It is defined as the minimum energy required to remove an electron from the ground state of a gaseous atom. Now, remember, electron affinity is the amount of energy that's released when you add an electron. Now we're removing an electron. So they're very similar and just pretty much the opposite. One of the major differences is with ionization energy, we're going to cover additional ionization energy. So when we think about like I1 here, this is when we're removing that first electron from a gaseous atom. In the case of potassium, we have gaseous potassium. We remove an electron, it becomes K+ in the gaseous state, and ionization energies are always positive. This is an endothermic process, removing an electron. We got to put energy in to pull that electron away from the nucleus. I2 would be, hey, now we're going to remove another electron. In this case, we're actually removing it from a positively one-charged ion. So if we wanted to do an example of this, K+ goes to K2+, and we form another electron being removed. Notice the energy required to do that is much, much greater. The reason for this is because that second electron that we're removing is a valence electron, whereas the first electron we removed is not a valence electron. In other words, this is an outermost this is a core electron. It's within the inner shells of our electron configuration, whereas this one's in the outermost shell, so it was easier to remove. And this actually gives us some important ability to be able to determine how many valence electrons an element has from ionization energy, because we see this big jump here. That's going to be the first core electron being removed.
But let's talk about the ionization energy trend. So if we look at a periodic table, ionization energy increases as we go up and to the right. And you kind of think about this as size, right? If you've ever played with magnets, the further you pull the magnets apart, the easier it is to have them stop attracting to each other. So something that is very large, for instance, something down here like francium, its electron is so far away from that nucleus that it's a lot easier to remove it. Whereas something like fluorine that's pretty small, the electrons are really right next to that nucleus and therefore are much harder to remove. And again, this is a trend you should know. You should be able to put things in order of increasing ionization energy, or pick out of a selection of them the largest ionization energy. But there's another fun thing we can do with ionization energies as well. So let's look at a graphical representation of the ionization energies for magnesium. And you can kind of see, like, hey, we have our first ionization energy here. It's probably like maybe 800 kilojoules or so. We have this one. Now we're looking at probably, I don't know, a good 1600 to 2000 probably kilojoules. But then look what happens on the third ionization energy. So the first one, right, losing the first electron. Second one, now we've pulled off a second electron. And the third, now we're at like, probably around 8,000 kilojoules per mole, give or take. Well, that's a pretty big jump going from 16 to 8, right? The reason why is because magnesium, if you look at how many valence electrons magnesium has, is it has 2 valence electrons. And if it has 2 valence electrons, then that's why these first 2 ionization energies are so much lower than the third, because the third ionization energy is the first electron that we're removing that's not a valence electron. And so if we look at another graph of this, we can kind of see this replicated in other elements. Aluminum has 3, I'm just going to say VE for valence electrons, and you look at the first 3 ionization energies, and they're relatively low when we compare that to the fourth ionization energy. And that's because this fourth ionization energy is the removal of a core electron. So let's look at one more. Here is a graph for element X. Given information like this, like for instance, if I gave you the first or a bunch of ionization energies like this, I probably wouldn't do it as a graph. I'd probably do it as like just numbers, like, hey, ionization energy 1 is this number, 2 is this number, and so on. You should be able to tell me, great, how many valence electrons are in X, right? And we can see that because between 4 and 5, there's this huge jump between those two ionization energies, that 4 must have been the last valence electron. And this fifth electron that we're removing is non-valence. This tells me that our valence electrons in whatever this element is 4. I could also say something along the lines is identify element X based on these if it's in the third row or the fifth row of the periodic table. And then you should be able to use these numbers to figure out valence electrons and then figure out which element in that row has that many valence electrons. Okay, so let's look at the ionic radii trend. The ionic radii trend is pretty much identical to the atomic radii when we're just comparing the same charge, positive versus positive or negative versus negative. However, something interesting happens when we look at positively charged things versus negatively charged things. So here is a lithium radius, right? And it's 152 picometers. When you lose that extra electron, that radius gets cut in half. Now we're talking about something that's only 76 picometers. This is a big difference. In fact, all positively charged things shrink in comparison to their neutral radius. Okay, so the larger the positive charge that our ion has, the smaller the radius will become. And this is mainly because as you lose those electrons, the remaining electrons in the atom are going to feel even more attracted to the nucleus because the positive charges aren't changing. The opposite is true for negatively charged things. As we get negative charges, our radii increase. The extra electrons need to spread out further because they don't want to repel each other. So the more electrons we add to an atom, the size of the atom's going to dramatically increase. And this is the main thing you need to know about ions versus atoms. Positively charged things are going to be much, much smaller, and negatively charged things are going to be much, much bigger. And the larger your positive charge or the larger your negative charge, the larger that ion is going to be, or smaller, in terms of, the larger negative charge, the larger it's going to be. The larger positive charge, the smaller it's going to be.
Okay, so let's cover the very last trend that we are going to cover, which is metallic character. And metallic character is pretty much what it sounds like. This is how much an element behaves like a metal, right? The more properties you have that are similar to a metal, the larger your metallic character will be. Now, what is our trend for metallic character? Well, as we know, metals tend to be on the left side of the periodic table. Non-metals tend to be on the upper right side of the periodic table. So that is in fact our trend. Metallic character increases as we go to the right and as we go down, right? So increasing to the right, increasing down. As you progressively go further to the right on the periodic table and further down on the periodic table, your element's going to have properties that are much more similar to what we consider to be the ideal properties of a metal, such as being malleable, having a low ionization energy, having a high melting point. These are all properties that are very consistent with most metals, and we're going to see more of those properties present in elements that are further to the left and further down on the periodic table. Okay, so one last little bit talking about trends in reactivity on the periodic table. This pretty much is that as we go draw my fake periodic table here. As we go from the center outwards, we see reactivity increase. And this is due to those elements wanting to get that perfect number of electrons. They either do it by gaining electrons or they get it by releasing electrons. And when they do that, reactions occur. So some really cool videos on this are when you watch like an alkali metal put in water, it actually explodes because it really wants to give away its electron, and it does it violently to the water. Whereas on the other side of the periodic table, we have like chlorine and fluorine. These are very dangerous, very reactive elements as well. And so they're over here, and the alkali metals are there. So you can kind of see as we go out to the sides of the periodic table, we see an increase in reactivity of these elements. All right, so if you guys have any questions, just let me know. I'm always happy to help. Please just shoot me an email, come to office hours, and I'm there for you.